So my name is, do this briefly first. So my name is Senso. I'm a commodity trader at Trafigura. We are one of the largest physical commodity traders in the world. I'm usually involved in the oil and metal side. In addition, I'm also the co-founder of Nomadic Powerbox, a startup focused on off-grid mobile renewable energy solutions. My background is in finance from George Mason University in the US, and today, as you'll see, we'll discuss a bit about energy. This map is an image by the NASA, and I think it's a very clear and visual representation of the world as it is and the importance of energy to the prosperity of nations. So for centuries, biomass was the main source of energy. Wood, animal waste still is to many places here as well. Coal started to make its mark 150 years ago with its steam engine. And as of today, the world is based on oil, coal, gas as the foundational pillars. So the above section are the main fossil fuel benchmark prices in the world. So when discussing price, you have to have three elements: what it is, where it is, when is it. Without these, you cannot get a price. And I'm not sure if the graphs aren't a little bit smaller, but I think it's obvious that the volatility of oil, natural gas, even coal has been extreme, impacted by geopolitics, resource dependency, whereas the graph for renewables are driven by technology and deployment. In the past 2 decades, solar utility scale solar has dropped 91%, wind a little bit less, 17%, lithium-ion batteries 90%, and it's every year the cost reduction is underestimated by analysts globally. So this is a snapshot of retail electricity prices around the world. It's a little bit old, it's in March, but I think you can get the sense that Mongolia is effectively in the lowest 20th percentile in the world as far as electricity rates. Now, this is by state control, hidden subsidies, keeping our rates artificially low. We're lucky we're not in the UK, Italy side. Okay, so let's take a look at the cost of energy in a little bit more depth. So the technical name is levelized cost of energy formula. So it is by combining the capital expense, the operating cost, the financing of it, fuel cost, any decommissioning cost, and subtract any tax benefit. Now you have to combine all these costs throughout the project life and divide it by the total electricity produced over its lifetime in present value terms. Now for the finance audience, present value is hugely impacted by the discount rate. So what is the discount rate for Mongolia? This is usually outsourced to the junior analysts on the job. One of the best metrics is to use the country's bond yield subtracted by the US bond yield in the same maturity. So it's the same in dollar terms. You get the true net risk premium of the country. This is in the past 10 years. It's been a volatile ride, anywhere going from investment grade to junk bond status at certain points in time. So when financing a project, when is of course a critical factor. Now, let's look at some of the assumptions. This is in the US for utility scale solar wind in the Midwest, diesel, fuel oil, or mazut for some of you. It's natural gas. These are what we call dispatchable. You can turn on and off whenever you want, whereas coal is the principal base load in most countries. Now, what are some of the key metrics I try to show? Some of them is the capex, dollar per kilowatt. So solar around 1,000, wind 1,500, diesel is pretty cheap, fuel oil, it's all right, it's competitive as well as natural gas. Coal is coming out in the US at $3,500. And another key element to look at is the weighted average cost of capital, or the discount rate. What is the discount rate people are charging to deploy these technologies in the US? And one of the principal figures to look at is, of course, the equity IRR, or equity cost of equity. How much investors need return in order to deploy these capital in the US? 4.3 is an astonishingly low number, frankly. It's one of the reasons why the levelized cost of number appears quite low. It has nothing to do with the actual electricity produced by the generation. It has hugely to do with the cost of capital used to deploy that. And for now, in real terms, all discounted back to present value and meeting the 5% goal, 5% cost of debt, assuming 70% for all projects as a leverage. You get these figures on top. 4 cents for renewables, 8 cents for natural gas at this current level, coal, 23 cents. It's about $50 per ton for coal in the US, by the way. Okay. Same metric, same methodology in Mongolia. What is different? Okay. Solar cost is about the same in the US because solar panels can be transported easily in containers, whereas giant wind turbines cannot. Diesel fuel oil generators are about the same, natural gas as well, whereas coal, everyone assumes at the moment $2,000 per kilowatt hour for a variety of reasons. Now, same methodology, same debt structure, but higher cost of capital. I believe we got at least 8%. Cost of equity in dollar terms, Mongolia, 14%, based on outside sources, but you can have your number as well. And roughly, the costs are and the costs show up to about 7-8 cents in South Gobi. Diesel is about 63% if you look at the total cost. When most people say diesel generators are cheap, they only look at the fuel cost. They do not look at operation and maintenance. The equipment itself is very cheap, whereas coal, same structure. Well, when politicians say our coal price is cheap, they are only referring to the spot cash operating cost of that coal, not the capex, not the financing, not the decommissioning cost. Now, if we include carbon cost on top of this, the difference becomes even more obvious. Okay. Wholesale electricity rates vary in developed nations. So let's look at California as an example, one of the extreme cases. They're famous for their California duck curve, when during the daytime, there's no net demand because they have so much solar panels deployed. Whereas the price, as you can see, it's a bit small, I understand, sorry, but during from midday to about 7, it's quite volatile. And right around the peak, when everybody goes home, makes dinner, cooks, showers, is the highest peak. Japan, wholesale electricity price, this was a spot price in July 31st, if I remember, yes. So the price as well, you can see it's quite volatile. Can go anywhere from 8 yen to up to 30 yen per kilowatt hour. Whereas Mongolia's system is much simpler. It stays the same no matter the day, no matter the season. Something is obviously not right. Okay. Storing energy is essential to make the most of any source, particularly renewable. So depending on the use case, the frequency and the duration of how much energy storage you need, the cost will also vary, as well as the different solutions to it, what type of batteries you want to use, what type of technology you want to use. So this is in the US, just to give a reference as far as the, so it's simple storing energy during nighttime or daytime, deploying it when it's best, or frequency controls, or emergency. There's a variety of uses of energy storage these days. You can go to this website. We'll share the presentation afterwards and input your number to get the levelized cost of energy storage for your project. According to McKinsey's Net Zero Heat Report, 50% of final electricity use is heat, 50%. Whether it's for high temperature, making steel, concrete, or basic home heating. If we do not address heating globally, we will not decarbonize. This is a bit busy graph. You don't have to look at all of it, but modern chemical batteries have been around 200 years since Volta's first pile battery. Amongst them now, lithium ion, which is this graph, is around $200 per kilowatt for electronics. This is pumped hydro, this is lead acid. It hasn't really improved much with more deployment. Whereas heat batteries are not talked about as much. They have their downfalls, but also, as well as their benefits. Depending on the duration of how much energy you want to store and the temperature, there are different types of material. So we'll go in depth. Okay. The simplest heat battery is in the gym at a sauna. You take electricity, you make heat, and you store it in the rocks. That's a heat battery. Now, and more advanced versions of that are different materials, so you can charge it by electricity or mainly by waste heat. So the waste heat can be from any source. It can be from wood stoves, diesel generators, heat pumps. It doesn't really matter how you get the heat. You can charge up the battery electrically or by heat and then use it later as heat if that's the main purpose. Okay. This is a snapshot or my recreation of it. Again, all my information are public, so and we can get the citations for it. But different materials are being tested throughout the world and are at different levels of technology readiness. And the costs as well as of today and in the future what it could be. But the main thing I want to emphasize is that it's the long-term asset. You can use it for 20, 30, 50 years without degradation. Chemical batteries cannot do that. Now, the main downfall is that when you give electricity to heat and then back to electricity, you only get 50% round trip efficiency. But if the goal is to use heat, then you get 90% round trip efficiency as far as use. Okay. Let's look at some real world examples. This is just, it's a very busy slide, I understand, but just talk a little bit. So on the left hand are some potential solutions that are on the market right now and also in development. So the first thing is what you call phase change material. What is phase change material? It's just basically wax, as a simple term, and used. There are UK companies, Netherlands companies, US companies, Israel companies, all engaged in thermal energy storage. Everybody is now looking to deploy and develop this technology. For example, my company, Trafigura, invested in Malta, a US-based startup, which can store 100 megawatts for 10 hours. Just to give a reference of how much energy that is. It's basically 10% of this entire country's grid capacity. We can provide that for 10 hours straight at very low heat loss rate. This is being developed. The first unit will be deployed in Canada and Spain in 2024, whereas some of the smaller units of this household are already available on the market today, you can buy. So for example, a 10 kilowatt hour energy storage battery will cost about $4,000. And there are many others engaging, using volcanic rock, bricks, molten salt, aluminum, concrete, graphite, all forms of liquid air. This is another UK company engaged in very large-scale energy storage projects. So we all know about UB's pollution challenge, and the current efforts aren't really making any progress. I've been waiting 33 years and still waiting. But UB is not like other highly populated cities. It's not Beijing, it's not Mumbai. It's 265,000 households without connection to central heating. It's a solvable number. It's a solvable level. So based on IRENA's International Renewable Energy Report, the Gear District, a household needs about 100 kilowatt hours in January. So this is quite a lot of energy demand, but it's also somewhere in the same park as Alberta, Canada, which use 82 kilowatts per day of energy storage, and about 2.5 times more than the UK. So if all the Gear District households installed a simple 10 kilowatt hour thermal energy storage, it needs about $1.3 billion funding. We can raise one green bond and deploy every household with potential heat battery. And if the savings just on the carbon credit or carbon credit revenue is 6.5 million tons a year. So the carbon price these days go anywhere from $10 to $100. So in the positive scenario, half of this $1.3 billion could be recouped just on the carbon credits alone within 2 to 3 years. Is the concept of storing heat in rocks a recent development? During the times of Hunnu and Chinggis, the architects were building underground air heating systems, similar as the Korean and Chinese. Strangely, this method has been lost by modern Mongolians. SunEdison is a US company. They are famous for deploying residential solar in the US with their no money down lease structure. So instead of worrying about how much power you get from, or what the power rate you get from the grid, they offered a deal where no money down, no cost of installation, but you pay fixed rate for 20 years to them and they will service you. So they took all this small revenue streams, combined them into a syndicate, turned it into a security, and got long-term capital financing to match, essentially a mortgage-backed security in the finance realm. The same can be applied to heat batteries. Again, these last for 30 to 50 years. And one day, even if we be a bit creative, we can have private utilities who can build their own private heating network to supply to commercial uses. So this is a slide by Irina as well. They identified the practical steps that we need to do in order to move the technology forward, from initial idea R&D stage to demonstration, deployment, commercialization. So what have we done recently? Well, we have passed a resolution to give 90% tax credit on the corporate income tax for power generation above 5 megawatts and 1.5 for heat. But this only lasts until 2029. Whereas the US, when they passed the Inflation Reduction Act, they are giving 30% investment tax credit. So any project, any battery you buy, you give 30% of your money back from the US tax credit. For companies, for engaged in large-scale projects, they are given up to 50% investment tax credit. 50%. If you hire the right people and make your project in certain areas and use domestic content. But 30% is the base, and it can go up to 50%. Coal has a long history, dating back 6,000 years in China, and the Industrial Revolution and beyond. I think some people think of the world now and wonder if it really needs to change. I think we can do a lot better. This is a typical power plant schematic. What is that? It's a coal boiler, effectively boiling water to make steam, go through the steam turbine to make electricity. Some of the heat goes to the heating networks, cool down, come back throughout the cycle. So my father was a thermodynamic engineer in power plant number 4. With modern solutions, we can replace the coal, the furnace section, while keeping the rest of the system. So people who are engaged in electrical engineering, steam pumps, systems, mechanical are all still useful skills. And I think we can make a push on policy to attract investors, companies, and to have the energy transition and be a bit warmer city. Thank you.